Good afternoon, everyone. I hope you are doing all right and ready to review. Today is our review day. Let's see what are the things we can review. So it is not going to be comprehensive. It's always good idea to go back and look at the materials we have learned. Uh, I think most, let's say, best thing to do is to go through the whole notes and learn inside out. But in the announcement, hopefully you saw the announcement. I have suggested some of those things that you can do. So we started this class talking about charges. So charges, they have mass and the charge, right? So in physics one, we talked about objects, things. They can move and do things. So they had mass, but they did not have charge. And the charges over here we are talking about, mostly they have very small amount of, you know, if we talk about, let's say, just electrons, protons that cause a charge, they have tiny mass. So often the mass, they don't appear in our description here. But charge plays large role, okay? And so that's why the name charges, okay? So we talked about how like charges repel each other and unlike charges attract, right? And we can make some, the atoms themselves or the materials themselves, they are neutral, but we can charge them by using one friction method. You rub something with the another thing, and then what happens is some of the electrons get transferred to the another object. So from where the electron leaves, there is deficiency of electron, means there is net positive charge, and the one where the electron went, it has now extra electrons, means it has negative charge, because electrons, we say electron has negative charge. Okay, electrons have negative charge. And that's charging by friction, and we can also just charge by conduction method. So for example, if we bring a charged object, let's say this is a conductor, and there is something like this, which is, let's say, negatively charged or could be positively charged. If we bring this into contact, direct contact, if this is conductor, then what happens? Some of the charges, for example, in this case, these negative charge means extra electrons. Those electrons move and they spread around, okay? So it becomes charged with a similar charge. If there is positive charge, then rather than moving this positive charge over there, because positive charge is in the solid, they don't move, rather electrons from the conductor, they arrive here, leaving this deficiency in charges. Okay, so deficiency in negative charges. So that means it becomes positively charged. It may seem like, okay, this positive charge moved here, but the negative charge moved here. So when object is neutral, that means there is no net charge, but there is still so many electrons and protons, positive charge and negative charges, okay, billions of them, okay? So when we say something is charged, we're talking about just the extra charge, okay? And the another one is induction method. So we can make charge, something we can charge without touching it. So I have another slide that has that induction setup. So we'll talk about that. But sometimes we can temporarily, let's say, separate the charges in a conductor or even in an insulator, okay? That process is called uh, polarization. So it develops poles of positive and negative charges. So neutral object looks like this. So basically, this is copy of that. So now let's suppose I have this positively charged rod. So if I bring this closer, when I bring it closer, see I'm not touching it. So what happens? The negative charge gets attracted, so there comes close to that. So one side net negative charge, other side net positive charge. But overall, there are still same number of positive and negative charge because none of the negative charge is skipped from here or get in there. So that means there is no charge transfer here. So net charge is still zero, but they align themselves so that it creates two poles, positive and negative pole. Okay. So that's why we say, okay, this is now polarized. Okay. So now the induction is another method of charging. I talked about charging by friction and conduction, and induction where we don't actually bring it in contact, rather we just bring it close. So see how it is polarized, just like I said. And in my drawings in the note, I don't have these bases, okay? But see, these are conductors, so you cannot touch directly. You have to touch with some sort of insulator, okay? So plastic tongue or something like that, okay? Which I did not draw. That's tough to draw, so I did not draw it, okay? So that's that. And then now we can briefly connect with a conductor or touch with our finger because our body is also conductor and it has a lot of charges, okay? Just like ground has a lot of charges, both positive and negative, a lot of charges, okay? So now when we connect to the ground with the wire, what happens? In this case, there is this positive charge in the side, means negative charge from the ground gonna go and combine with them. They say, oh, there is attracting. This is very attractive. Let's go. And that's how they combine and they neutralize the positive charge. But these being negative and negative are there, so they do not want to mess with the negative, right? So that's what happens. And next, if we want to charge it, we still, while this is still there, you will need to disconnect it. So it's going to be just brief connection, okay? Just brief connection. If you are touching with your finger, just a single touch, little touch, gonna be enough. Tenth of a second, 1 second, good enough. You don't have to have long time there. And what happens after that? You disconnect that. They are still attracted there. This side became neutral. So now, see, there is now extra negative charge. Okay, so if you remove, when you remove this rod, then now what happens? Oh, suddenly there is a lot of repelling charges together. So they're going to spread and going to be something like that. So this becomes negatively charged. When you bring positively charged rod, it becomes negatively charged. But if you were to bring negatively charged rod, I guess this would be positively charged. Okay, so kind of it gets oppositely charged. So we cannot charge insulator using this method because these electrons, this has to be conductor. Okay, so if you want to charge insulator, best bet is just friction. Okay, and little bit polarization, we can do that, but not a lot of chance we can put in insulator. Okay, so now I have a question for you. So let's suppose I brought this, and by the way, this is review, means all of these slides, I think you have seen them, okay? If you did not miss the class, or if you look the posted slides, okay? I just picked some of them to give you the important information. To review means revise the main things we have learned. What did we learn in this class? Charges, I started talking about, and then we talked about property of charges, how they attract and repel. And then that attraction and repulsion means interaction between them. So there is force involved, and force can be calculated by using this, let's say, product of charges. I think we wrote in the formula something like this, right? So this is separation distance between charges and so on. So we talked about force, and then we talked about energy, and then often rather than talking in terms of kinetic and potential energies, we talk in terms of potential. And we also talk in terms of field. So force, field, potential energy, they are related. So do you know how they are related? Maybe you want to learn them, okay? So anyway, so those are the kind of things we learn. And after that, we started talking about circuits, right? Current, when charge flows, and then circuit and how to solve problems in the circuit. So those are the things we have learned so far in this class. So you will be tested on those things. Okay? So I made the questions. So there are 30 questions and I'll be counting base 25. So there is still going to be 5 choices. Okay. But in physics 1, if you took recently, if you took a lot ago, then I may have given you 30 questions, but for the recent semester, I had 25 questions. So now I have 30 questions for the physics 2. You folks are grown-up folks, you should be able to handle more questions, okay? You grew up from physics 1 to physics 2, right? So anyway, so that's how the test's gonna be. So now let me pull on this one here. 30 more seconds. Okay, 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do here. So looks like C and E competing, positive, negative versus 0. So when it is near there, what happens? Just like we saw, they're going to be this and they're going to be this, right? When it is there. So what we are doing is very important. The charge rod is brought near. So when it is near, it is like this. Now, then the charge rod is then removed. So now, once you remove, once the charge rod are not there, since they are still in contact and they are conductors, what happens? They're gonna basically recombine, okay? So becomes neutral because they are separating charges. There is the separation of charge because of this charge rod being near, right? Once it's gone, this is gonna be just neutral. Now, once you separate, basically you are just separating the neutrals one. So this is going to be 0. So yes, E is correct answer. But if you chose C, most likely you are just thinking of this. So if you were to remove without, if you were to remove this before removing the rod, Then there would be positive charge on this and negative charge on this, okay? Then C would be correct answer. If we were to separate these before we remove this, then that's going to be that, okay? Now, let's say if you were to touch, then these electrons are going to jump here, leaving touch and remove. And then in that case, they're going to be positive charge here and positive because some of the negative charge is going to go to the rod, okay? Because rod touched it. So they're going to be net positive charge. So it depends on how, what happened there. Okay, all these steps matters. In what order, that matters too. Okay, now here is another question related to force. So force between two charges. So over here, one charge is uppercase Q. All of those, this charge is same, but other charges on the other side, let's say test charge, we are changing them. So we are bringing different amount of charge at different distance and testing the force. So what do we expect, right? Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So which experience the largest force? So this is largest charge, experience largest force. Makes sense? But does it? Okay. So for that, we have to actually use the formula. So whenever formula is available, whenever you can, use formula. Don't use your gut feeling. Okay. So in this case, if I were to write this formula, over here is going to be K, Q, Q, distance is R, so R is squared. So that is the force between these two. Now, what's the force between these two? K, Q, to Q over R squared means here, this is 2. So that means 4R squared because 2R squared means 4R squared. Okay. So square of this means 4R squared. I think that's going to be easier to tell. Okay. So now what do we see here is, this is, if I were to cancel this 2 over there on the top, it's going to be half KQ, Q, charge is there, and R square. See, this is exactly half. The force on 2Q is exactly half. Now, on 4Q, we have, let's do the same thing, K, Q, 4Q, and then 4R square, because distance is still 2R. So now it cancels. So it looks like this is simply KQ, Q. Oh, 1Q is little q. Okay. So yes, looks like this and that gonna be same. They are exactly same. So double distance decreases force by a quarter, but 4 times charge increases by 4. So 4 and quarter cancels, giving the same. So Q and 4Q experience the same force. Okay. So this is force. And we can calculate field over here. If we want to find field over here, we don't need this, right? Field is just KQ over R square. So we don't need source charge. So field can be anywhere. As long as we have a source charge, we can have a field due to that source charge at any distance, okay, from that. And the formula for the field is this. Did I hear sound? Yeah, feel free to ask if you have a question.
I have a question.
Yeah.
So instead of doing it like that with the equation, would it be easier to just think of it as since the R doubled and the charge quadrupled is technically the same
Yeah,
force? Okay.
that's the smart way to do it. But we may make mistake, okay? But I'm not as smart as you are, so that's why I like to use formula so that I'm not making mistake, okay? So yes, that way is good and quick. If you are in rush, that's what you need to do. But if you have time, yes, do that and also use formula to check, okay, systematically. So over here, there is this point over there. So there is no charge. So there are these charges that's shown. So now it's asking about in which case is the field on the dot the largest. And all the charges have equal value. What value they are, I don't know. Probably we don't need to know. Okay. Okay, let's do 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see how did we do here. So mostly A, but there are quite a few C as well. So in this case, see in the last case we had like it's the force between two charges. So we use, there is just one force between these two charges, and that force is on this, and the same amount of force is also acting on that, okay? Like an action-reaction force. Now, field at this point means now the field gonna be from here and there. So same thing goes with the force as well, of course. Oh, at this point, there is no charge, means there not going to be any force at that point. Okay, but they're going to be field. Okay, and so in that case, now there are two charges. We need to draw or figure out field due to both of them and add them vectorially, right? Field, they have both magnitude and direction, but in this case, this is going to be either towards them or opposite to them, right? So for the field, by definition, we assume that the direction of field going to be same as the direction of force experienced by a tiny positive charge over there. Okay. So when we are calculating field, we can assume there is tiny positive charge to figure out the direction of field. So in this case, what happens? There is this, let's say this negative charge. So the field gonna point in that direction, because if there was tiny positive charge there, positive and negative, they attract each other. So since we are interested in field at this point, it's gonna be like that. So let's say this is field due to negative charge. Okay, I'm not saying negative field, I'm just saying field due to negative charge. Okay, so now positive charge, on positive charge, what happens? Repulsion means field gonna be in that direction as well. And both of them are at same distance. This point is at same distance from both of them. So that means the value of this field and that field, they are same. And also the direction. So since both of them are pointing in the same direction, it gets added. So net field gonna be a positive. And since both of them are pointing this way, if I say that is positive, then I can say positive and E negative. And remember, these are just the notation. I could have said E1, E2, okay? So I could have done that, but here there is this negative charge. So I said, okay, that's negative, just a notation. But this is sign for the algebra. But this is just a notation, okay? So both of them have same value. They are pointing in same direction. So they gets added. So this becomes, oh, same value. So let me just write the value. They are same. So I can say, okay, this is positive 2 times E, where the value of E is same as value of that. Okay. So that's why I said, okay, I can just write this because they have same value. So I can say, okay, it's double over there. So now using the same logic, over here, what do we find? This negative is attracting here and it's closer. So it's going to have larger force. But this one is farther, and positive means it's going to be in opposite direction. That is, let me just write negative for that, and this is going to be positive. So this is shorter, smaller than this one here. Now, if we look at this, okay, both of them gonna push, but this is gonna push harder than that one, farther one. So this is gonna be only about quarter. So this E plus, its value is different. So I guess I cannot write both of them as a plus and plus. So let me write E1 and E2. So E2 gonna be just a quarter of E1 because it's a double distance. Okay, so that's that. Over here, what happens? It pulls that way. This one pulls that way. Tug of war. And so that means both of these have equal value, but opposite sign means E net is 0. So looks like although these two are pointing in the same direction, one being bit smaller than the other, the total or the net here is not as big as in this case. So yes, A is correct answer in this case. Okay. Okay, so that's value and direction of field. And then we also learn about field lines. So what did we learn about field lines? So field line, so there is a question, good question on that on the Zoom. So do we always assume that the little dot has a slight positive charge to find the direction? Okay. To find the direction of field, you assume like that. Okay. But it's not there though. Keep that in mind. Just to find the direction of field, we assume that. But it's not there when it says it's just a point. If it says point charge, then it is there. But if it just says point, then it's not there. Okay. Okay, so that's that. Now, field lines, basically they originate from positive charge and they terminate on the negative charge. Okay, so that's how they work. And larger value of charge. So for example, if I were to suddenly double this charge to 2 times Q, then they're going to be, we represent that by dense lines. So double the number of what we had before. Okay. So that's the double going to be the field lines coming out through the same area. Okay. And from the field lines, if you have just field lines, we can, and of course, the field line always goes from positive towards the negative, but it is path followed by that tiny charge, assumed tiny charge. So this tiny charge experience force from both of them. Because of that, it's not always moving straight. Only the one that is right there gonna move straight there. Others, they're gonna be curved, okay? Because when that tiny charge is close to this positive charge, it experiences large force away from it and tiny pull from this one there, okay? Pull from that one gonna be tiny. So this one is winning, so that's why it is moving more in that direction. But there is little pull, so that's why it's also turning. By the time it arrives here, now what happens? There is equal force, and then uh, it kind of crawling in that direction, and then it starts, the force because of this becomes now larger because the distance is larger. So because of that, it's gonna go directly towards that direction. So that's why the field lines look the way they look. And from the field line, we can find the direction of electric field by drawing tangent line at that point. Okay. And here is a question. So I have drawn few lines at that point over there. And those A, B, C, D, E are the choices. Okay. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. So we see mostly C, but there are quite a few B as well. Okay. Field line, sorry, the field direction is tangent. So these arrows you see, they are not actually direction of field. This simply says, okay, field line is going something like that. To find direction of field at any point, you need to actually draw a tangent line at that point. So this arrow would mean the direction of field at that point is in that direction, okay? If I was talking about this point, then this would be something like that, okay? Right there. But since I'm talking about this, it is pointing towards that, see, negative charge. And since it is exactly in between, what happens? This is horizontal. So C is correct answer. And this kind of setup of charge is also called dipole. And in class, we did actually draw the fields uh, due to both of these charges. Like this one, the field due to this going to be pointing this way. Field due to this going to be pointing that way. But so yes, and they have equal values because they are at equal distance, right? If I am talking about this center point there, the sum of these two gonna be in between them exactly. Or you can just use the vector addition method, bring the tail of this E1 or let's say over here, and the net gonna be that, and that's what we're talking about, okay? But we don't need to do this if we remember this property that, okay, the field at a point is always tangent at that point, okay? So how do we draw a tangent line? It just passes by just touching that point, okay? So in physics 1, we learned that we can put a dot next to it, right next to it, and then draw a line passing through that. So that's going to be tangent. And how do I know it's pointing this way, not that way? Because see here how the field lines are going. Based on that, I can tell it's going to be pointing this way, not that way. Okay. Okay. So force, field, and then after that, work, energy, potential, right? So those are the things we learn. And here, that's what I'm talking about in this slide. Let's forget about this for now, okay? So what is the direction of electric field between the charge plates? Here are the plates. And here it says towards positive charge means it's going like that. Towards negative charge means it's going like that. So which one is it? So that's what I'm asking. Okay. So I'm opening the poll and you have a minute to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So just like we saw, field lines goes from positive to negative. So this would be field line. In between the plates, what happens? They go straight. And we learned that in this kind of configuration, field is constant. It's same everywhere in between the plate. Okay. So field goes from positive to negative. And that we can tell by saying, okay, if I were to bring tiny positive charge, it's going to get pushed and pulled this way, right? It's going to move that way. So here, field line are a straight line. So field line and field electric field, they're going to have same direction in this case because they are not curved, means we don't need to draw a tangent line. Okay. So that is the direction of field. So now I have another question here. What is the direction of force on a negative charge, right? So if I were to bring a negative charge, let's say somewhere in between, what's going to be the direction of force? So I'm opening the pole. Thirty more seconds. Five more seconds. Five, four, three, two, one, and it stops. Let's see what we got here. A towards the positive charge. So yes, negative gonna. Did I choose the correct answer on that one? So for the previous question or this question, the correct answer was, so what is the direction of electric field between the charges towards negative charge? So yes, that would be B. Okay. Field is pointing down. Force is on the charge. So now field, it's the field. There is no other charge other than the source charge. It does not matter. It's always, it starts from positive charge, okay? But force, for the force, we need another charge, means the sign of the other charge is going to determine what's going to be the direction of force, okay? So negative charge gets attracted towards positive charge, of course. So that should be obvious, right? It gets pushed by the negative charge and pulled by the positive charge. So here there were these positive and negative charges. But let's say if I gave you just the, said, okay, this is the electric field. Now, what is the direction of force on negative charge, right? So if I say that, can you tell what is the direction of electric force, right? So for example, here. So let me quickly make, so let's say this is A, this is B. So what is the direction of force on negative Q at the field E? Okay, so direction of field is known, right? And we know there is this negative charge here, let's say. What's going to be the direction? Oh, we can have up or down. Almost forgot. Okay. So I'm opening the poll and you have 30 seconds for this. Okay. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. Oh, what happened? What happened? Okay, I think that was that. So correct answer in this case is A. See how the negative charge. For a moment, let's say you know the field, but you don't know the charges. Then which way is this force acting on it? Opposite to the field, right? So on negative charge, force is in the opposite direction to the field. On positive charge, that's the direction of field. And being negative, it's exactly opposite. Okay? On the positive, in the direction of field, and that's how we determine the direction of field. So that means force is going to be in the direction of field for positive charge. On positive charge, let's say if that was that, then force would be the same direction as field. But on negative charge, it's going to be opposite. Okay? So that's how it works. Now, with that, now let's move on here. What is the work done by electric force on charge negative Q? So in this case, the force is in that direction. So if it is just moving in, so if there is no other forces acting, then of course it's going to be accelerating in the same direction. So displacement also going to be in the direction of force. So that means it's going to be f d cosine. And what's the angle between them? D is pointing this way, force is also pointing the same way, means the angle between them is 0 degree. Cosine 0 degree is positive 1. So that means the work done going to be positive F times D. Okay. What is the change in electric potential energy? So we just found the work done. And then for this, we have learned that change in electric potential energy is equal to the negative of the work done by the field. So that means in this case, it's going to be negative W, W being positive, it is now negative F times D. So this is the relationship between change in potential energy and work done. Okay. And now, how about potential? So potential energy, remember things move to in the direction of decreasing potential energy. Just like when we drop something, what happens? It goes down because gravitational potential energy is lower as we go lower and lower. So that means that's why the object falls on the earth, because that's where the lowest gravitational potential energy is. Actually, it's going to be in the middle of the earth, but since there is no more room for falling, there is no tunnel, it just stops on the surface. But in case of electric force, the idea is same. So if you see some charge is moving this way, so let's say if B is that, then we can say, okay, potential energy for that charge is smaller that way in the direction it is falling or moving. Okay, so that is potential energy I'm talking about. Now, potential energy has this equation. I think we wrote electric potential energy as K Q Q over R, not R squared. So R squared would be force, but energy is just that, because to find work done, see, we have to multiply with the distance. So one of the R goes out. So that's that. So for potential energy, we need this charge, just like we need two charges for the force. But for the field, we need just one charge, source charge, right? Same thing goes with the potential. So we don't need this source charge, let's say. So that means whether you bring a positive Q charge or negative Q charge does not matter. The potential at the potential positive charge is always larger, okay? So potential and potential energy, they are not same. Let me repeat, okay? So potential energy depends on source charge, but potential simply depends on, we use uppercase B for that, and it is just KQ over R, and over here we had another Q. So potential at positive charge is always higher than the negative charge. Okay. Why? Because when Q is positive, this thing becomes positive, so potential is positive. But when this Q is negative, let's say, source charge is negative, in that case, the potential becomes negative. So potential energy, they are scalars, they are not vectors. So negative sign actually means, less than the positive, like ordinary numbers, okay? So those are the things about potential energy, force field, and so on. So now here is another question. So this point is exactly at the middle between these two, okay? We already had a question about field in this kind of situation. Now we have also added the potential, okay? So let me open the poll, and you have a minute and 30 seconds to answer this question. 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. So now let's see what we got here. So we got kind of staircases here. So let's see. So electric field is better. So we can think of having very tiny charge over there to find the direction. And of course, the value is just comes from this. So this gonna push this way, and that one gonna push this way. So this field 1 and field 2, they have same value because same source charge, same distance. So that means they are going opposite to each other. So that means they're going to cancel. Same value, opposite direction. So that means they cancel and net becomes 0. So E net is 0. Now, how about potential? So potential is a scalar quantity, and its formula is given by KQ over R. So due to one positive charge, it's going to be positive KQ over R, and it does not have direction, so that's why we don't draw potential like that, okay? We just write numbers, right? And that is due to one charge, let's say charge number 1, and due to 2, it's the same thing, same distance, same charge, right? So B2 is also positive KQ over R. So that means V net is just the sum of these two numbers. So that's why the V is not 0, it's non-zero, but E is 0. So looks like A is correct answer in this case. Okay. So quite a few of you also chose B. That would be the case if E was not a vector and B was a vector. Hey, B for vector. Sounds like V is supposed to be vector, but V is potential, which is a scalar, okay? Okay, so we can use kinematics for the charges because charges, they have mass, so they can move from one place to another place. So how do we use kinematics for the charge? So we just use, let's say, we find the acceleration using force divided by mass or net force divided by mass. And then force for the electric charge is, if we know in terms of field, it's going to be Q times E over M, okay? Or depending on how many charges, let's say if there is only one charge that's pushing it, so I will just remove the summation sign, so that, or we can do K, Q over R square, right? It's the same thing. Here I wrote in terms of field. So force and field, they are related like that. Force is Q times E because this is how we define field. Force per unit charge is field. So that's why force is that, okay? So we can use kinematics once we have the acceleration, and the acceleration has to be constant, means to use, kinematics, acceleration has to be constant, means field has to be constant. But we can use conservation of energy even when the field is not constant. So for example, in this case, field is not constant, okay? So field is not given, rather potential is given here. So we can use conservation of energy. So total final energy is equal to total initial energy. That's the conservation of energy. So here kinetic energy, because charges have mass, mass times velocity squared, it can kinetic energy. And for the potential energy, what do? We define potential as a energy divided by charge, means potential energy is charge times potential. If we have potential difference, then we can find change in energy, potential energy, Q times delta V. Okay, so this is potential at a point. This is change in potential between 2 points. Okay, so for example, here there is potential given, there is another potential given. So we know the potential difference between the points. If we know what charge is moving, that means we can use just Q times delta V and find change in potential energy, which would be final minus initial UI. Okay, so we can do that. So that's going to give us kinetic energy or change in kinetic energy, because change in kinetic energy is equal to change in potential energy in terms of value. So when kinetic energy is increasing, potential energy is decreasing, and vice versa, because the sum remains same. That's what the conservation of energy is in another word. The sum remains constant. Sum at final point remains same as sum at initial point, right? And so what I'm saying is, if we are asked to find just the kinetic energy, we can just do Q times delta V and find the value of change in potential energy. And change in potential energy and change in kinetic energy, they're going to have, like let's say just the difference, like change in kinetic energy going to be same as change in potential energy. They will have different sign, opposite sign, but they're going to be same. For example, if I write this equation something like this, just pushing both of them on the same side, this is change in kinetic energy. This is change in potential energy. Oh, no, this is ui minus uf, but we need uf minus ui, so we need that negative sign. See how you can find the values by just finding one or the other. In this case, it's not asking for the kinetic energy, looks like. It's asking for the speed. So for that, you need to convert this into kinetic energy equation, or you can simply use this equation over here, right? So when it is released from point A, so let's say this is initial, and B, this is final, okay? So speed at A is 0, or I think I said initial, so let's write initial, okay? Because it says it's released from there, so that means it starts moving once you release it, okay? Then travels past B. What is the speed at B, right? So something like that is happening there. So that means we are asked to find final speed. So this lowercase b's, they are for speed, but there is potential. See, these are equipotential lines, and it says 60 volt here, means everywhere in this line here, everywhere is a 60 volt, means over there is 60 volt. And potential we denote by uppercase B. So initial potential is 60 volt. Okay. And final potential is 20 volt. And it is proton. So the charge that's moving is proton, means it has a positive E charge. And we know value of E is 1.6 10 to the power negative 19 Coulomb. And mass of proton, it's hard to remember, but I have given that one there, so we know that. See here, we know everything but BF, so we should be able to calculate BF, right? So over here, these would be the mass of proton, but this is 0 because initial velocity is 0. So you'll have just these three, okay? And you can see, you just move that this side, and it becomes just Q times delta V. Okay, so that's that. So that's how we use conservation of energy. And if we have to use kinematics, then we find the acceleration by using force is Q times E. Okay. Oh, it's 3:05. Let's take a break. Okay, welcome back, folks. So now I have another question for you. It's related to capacitor. So charge, this is charge in one of the plate of a capacitor, right? Something like that. So both plates have charge, remember, in a capacitor. One has a positive charge, another one has a negative charge. And this is called capacitance, the capacity. And that capacity simply depends on the geometry. And this is potential difference. So whenever there is charge, there's going to be a potential here, and there's going to be a potential over there. So difference between these two is the potential difference. Or let's say this is 1, this is 2, V2 minus V1, something like that, okay? So with that, now I'm going to open the poll. And you have a minute and 30 seconds to answer. Thirty more seconds. Five more seconds. Five, four, three, two, one, and it stops. Okay, let's see what we got here. So mostly D up by 8. Let's see if that's the case. So here A, area of a plate. So this L, both sides, they have same length. So that means it is a square plate. I can write something like this. So this is the capacitance of this plate. Now we are doubling L. So C nu gonna be what? This is still same, but the area is now 2 times L squared. And then D becomes D over 2. So this picks up a factor of 4. And there is D, and there is half. So this being fraction of fraction, we can bring it up. So this becomes 2 times 4, which is 8 times whatever we had before. So it increased by 8. Yeah, so D is correct answer in this case. So now, kind of similar fashion, but it says resistance and diameter. So we learned that resistance, last time I think I wrote wrong equation. So hopefully I don't do that at first. There, rho L over A. So that's the equation. Here again, this is area. This is length. Resistivity. And this is resistance. And area in terms of diameter, I think you know that, but oh, okay, so now I'm opening the poll and you have a minute to poll on this. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what happens here. So C and D kind of competing. So decreases to half or quarter. So here what happened? D double. D went to 2D. So area is in the denominator. So it's like saying, okay, I have pi d square and 4 is in the denominator. So it's going to go there. So it's in the formula. So this constant does not change. Resistivity for a given material does not change. So here, this is just a wire and its length is not being changed. So that means this one does not change. Pi does not change. So that means resistance simply depends on diameter. But it's not just diameter, it's a diameter squared. So since this is in denominator, when we square this, what happens? We pick up a factor of 4 in denominator. Okay, so looks like yes, it becomes to a quarter. Okay, so if this area did not have diameter squared, just diameter, then would be half. Okay, but since we have d squared, we need to square that half, and that thing is in the bottom. So 1/4 means quarter. Okay, so that's that. Now let's talk about power. Remember, power of light bulb can be written as I times V or I square times R or B square over R. And we may have written V as a delta V sometimes. That's fine. Okay. Here, basically, this V means potential difference. And home is America, by the way. We are in American side, not in Europe. 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. Oh, we have C and D competing, but we have all choices except E. So here a light bulb we buy. So same light bulb we are bringing here. So that means a light bulb has coil, has a coil, it has a resistance. So when you bring light bulb from Paris to USA, resistance does not change. Okay. So R is fixed. And if there is power and there is voltages, so resistance, power, voltage looks like this is the good equation. Okay. Because those are the things that we know. Okay. So in Paris, this is 240 volts. Outlet is 240 volts. And here in the US, it is 120 volt outlet. So what happened? V went to V over 2. You see that? 240 to 120. So now, how to find power? We need B squared. So B squared means this is squared, means B squared over 4. So it looks like the power gonna be quarter because voltage decreased to half. Okay? So our outlet is providing only half of the voltage that uh, Paris outlet provides. So because of that, what happens? Power now received by that light bulb gonna be quarter. So yes, looks like D is correct answer in this case. So it's not like a laptop, okay? So laptop has a adapter thingy. So you can provide a range of input, but output gonna be fixed. For example, if the output takes, if the laptop takes 24 volts, then the adapter gives just the 24 volts to the laptop, no matter how much input you are putting. And they have designed this to all the way from 120 to 240 so that the output is always same, 24 volts, okay? So that's how the laptops are designed, but there are no such thing as an adapter for the light bulbs. So what happens to them? Their brightness change. Power changes means brightness change, okay? So now here is now current question looks like, circuit question. So current past this is maybe IA. Current past C is IC. Okay, so that's what this question is talking about. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So mostly same current, and series means same current. Okay, there is no room for branching, so same current. So I just remember, so at the beginning, I showed this slide. Hopefully you saw this announcement I sent a couple of days ago, I guess. Okay. So make sure to you sign in using the SSO option that I have shown here. Seems like one or two of you is still not signing using SSO option. And another thing I like to point out is if you took physics 1 with me, we used to have worksheets. So here I did not assign you worksheets, but the worksheets from my previous class, they are still here. There? No? Oh, what is this? Yep, he's under the study guide now, huh? So for example, if I wasn't giving you playground, I would be giving this one, okay? So see how this thing works? So there are these questions. You can think of this as a practice question and do it and see if you can do them. You should be able to do it up to circuit. So that means 5 worksheets, 1 to 5 worksheets. Okay, so here is another question. So these two resistors are in series. Now it's asking what is the voltage across R1. Okay, so here we are connecting 12 volt. That's what it means when we write like this. Okay. You have 2 minutes. Take your time. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. Oh, we are all over the places. So now to find voltage here, see the resistance is known. So if we know current, then we can find, okay, voltage at that point is current at that I1 R1, let's say, and B2 gonna be I2 R2. But since they are in series, what happens? I1 is I2 as they are in series. So that means we can simply say I. So that means I times R1, I times R2. So that's how we can find the voltage. So now to find current, we need equivalent resistance of the circuit to find current through this whole circuit. So if the same current flows through all of these, they are being in series, right? And so if I go one step further, I can write this R equivalent. And since they are in series, we just add them 6 ohm. And the potential here is 12 volt. So delta V, or I think it says VAB, potential difference between point A and B. So the current now can be found by using Ohm's law because there is only one resistor now. Twelve volts over R equivalent is 6 ohm. So that means it's a 2 ampere. Okay, so we found the current. Multiply that current with the resistor at that point. So it's asking for R1 voltage across R1. So that means, so V1 is I1 or just I times R1 means 2 times 2 is 4 and volts. Okay. So it looks like D is correct answer in this case. So what happens here? Up to this point, we have 12. Over here, what happened? See, the 4 volt is gone, means now we have 8 volt. And over here is going to be 0. So difference here is 8 volt. And difference here is 4 volt. Okay. So that's how the 12 volts divides into 2 resistors.
I have a question.
Yeah.
Can I just do V times R1 divided by the total resistance?
Yeah, I suppose you can, but why are you doing that? Right? You have to explain to yourself, right? We don't have such formula, right? But eventually turns out to be the same thing, okay? What you are saying. So basically this, so we are multiplying this by R1, right? So that's what you are saying. Can I do that? So yes, looks like you can, but why? You have to learn logically do that, okay? Rather than just remembering, okay, I can do this. So now here is another question related to circuit. So current flowing past that means this and that, right? So these are the two currents we're talking about. So this is like saying IA, this is IB. So I'm opening the poll and you have a minute and 30 seconds. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, what did we get here? So we are saying A and B are equal. And then, yeah, we have all choices. So these are in parallel. So that means this one has 5 volt. This one also has 5 volt because this is parallel with this. This is parallel with this. And two of these are parallel with each other as well. So to find current, for example, IA, I can write, okay, voltage across A and C, for example, VAC divided by R1, right? So that's what this resistance we are told. So now BAC is 5 volt because this power supply is this and it is in parallel with that. So all the way here is going to be 5 volt. Over here is going to be 0 volt. So that means there is 5 volt there. So it's going to be 5 over R1. Oops, we don't know R1. And now for IB, I can do the same thing. BD over R2 means 5 over R2. So without knowing R1 and R2, we cannot compare I1 and I2. So looks like D is correct answer here. Okay. So when it's in parallel, you can just divide voltage by that resistor, okay? If there are just these two, right? But sometimes you may be given something like this, for example. There was one in the weekly, we did one in the class, right? So we may have something like this. So in that case, this voltage is not same as this voltage over here, okay? Because part of it drops there. So be careful on that. And we did Kirchhoff's rule. So potential difference, we count positive or negative depending on whether it's increasing or decreasing, right? Change, if final is less than initial, then difference is gonna be negative. But if final is larger than initial, then difference is gonna be positive. And we know this smaller line means lower voltage and longer line means larger voltage. And we also know current flows from positive terminal of battery to negative terminal of battery. Means positive terminal means higher voltage, and negative means lower voltage. So that means current flows from higher to lower voltage in the circuit. So those are the things you have to have in your head. So with that, I will let you pull on this one. I think total 1 minute should do it. 30 more seconds. Five more seconds. Five, four, three, two, one, and it stops. Let's see what we got here. So mostly B. Well, let's see. So we are going this way. So higher, lower. So going this way means difference is negative. And here we are going from lower. So this side is lower and this side is higher because current flows from higher to lower. So the difference is positive. So loop tells you which one is initial, which one is final, right? Direction of loop. So did I choose the answer here? I haven't. Okay. So now, how about this one here? Oops. Thirty more seconds. Five more seconds. Five, four, three, two, one, and it stops. Let's see what we got here. So mostly B, and there are some C. So all these starts from I2 R2. So I2 R2 is here. So loop is going this way and current is flowing this way, same way. So current flows from higher to lower. So this higher initial is higher. It is initial because we are going this way. It is higher because current is going this way. So that means difference in this case is going to be negative. So C and D out. Over here, we are going from positive to negative. So higher, lower. And we are going this way here. Higher to lower means it is also negative. Okay. This one, we are going in the opposite direction of current. So this is lower, but this side is initial for us because our loop is going that way, right? So this is initial, this is final. So when final is larger than initial, the difference is going to be positive. So that means it's a positive I1, R1. So it looks like yes, it is B. B is correct answer. Ooh. This should be easy. Let's try. Just find the equivalent resistance of these three. We don't have much time, so I'm just giving you a minute. Should be good enough if you know the trick. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. We got all of them. Slightly more for A, and A is correct answer in this case. See this 4 and 4, when we have equal in parallel, equivalent going to be exactly half. Now with that, we can say, okay, we have 1 2 ohm, another one 2 ohm. So that is 1, equivalent is 1. Or you can just use formula 1 over R1 plus 1 over R2 plus 1 over R3, and R1, let's say, is this, so that means 2 plus 4 plus 4, 1 over 4, I mean. So you can do, I guess, 2 over 4 plus 1 over 4 plus 1 over 4. That is 4 over 4. Oh, tough. So that gives me 1 over R equivalent. So R equivalent is just 1. Okay. Flip or not flip, it gives you the same result. Okay, folks. So I'll see you next class for the test. I have Zoom hour tomorrow. If you like to stop by, it is, I guess, what time? 10 to 11, 10 to 10:50, something like that.